go. Okay, good. So welcome everybody to the final installment of this term's fluid dynamics seminar at Imperial. We're going to end on a high note. We're going to have today as our speaker Bruce Sutherland from the University of Alberta. Bruce is an expert in internal gravity waves and all kind of other geophysical and environmental fluid dynamics. And today he's going to tell us all about rotating plumes and their possible transformation into tornadoes. Welcome, Bruce, and the floor is yours.
Thank you very much, Peter. I'd say it's great to be here, but of course I'm not there. I really wish I was. I have so many great friends and colleagues at Imperial College. But hopefully it won't be too long before we can all get together in person. In any case, so today I'm going to talk about some lab experiments and numerical simulations that were done on rotating plumes. To be honest, we started off this just by thinking, looking at rotating plumes, but somewhat serendipitously, we just stumbled on an interesting phenomenon, which is that sometimes this plume forms into a columnar vortex, and that's something colloquially I'm referring to as a tornado. In fact, so that was discovered by my PhD student, Yong Sing, but independently, Daria Frank, working with Paul Linden, discovered this in a completely separate set of experiments. And so that encouraged me to think it was my students screwing up, and this is a real phenomenon. So I spent a few months at Marseille University with Michael Lebar, working with his student Daphne Le Mascalier. And we didn't succeed as well as we tried. So then I spent another 4 months, both by the way, in the wintertime, not a coincidence. And I went to Lyon and worked with Thierry Duxois and Sylvain Gerbaud and his two students, Corentin and Timothée Jamin, where we finally were able to reproduce this tornado phenomena reliably. But in the end, as I'll show you, it's really numerical simulations that give us the information we need to understand what's going on. Okay, so you might ask, why would rotation affect a plume? After all, the time scales of turbulence in a plume is they're so short compared to the rotation period of the Earth. It shouldn't have an influence. But I'm showing you two examples here of that lead you into why you might think it might ultimately have an effect. It's not the time scales of the turbulence we care about, but the duration of the plume itself. If you have a plume that's ongoing for a period of a day or more, in these examples, the Deepwater Horizon oil plume at the bottom of the Gulf of Mexico, it was a plume that was rising for months. The issue isn't so much directly how rotation affects the plume, but how the plume is influencing the ambient fluid. And of course, the ambient fluid is very slow moving, slowly entraining into the plume, and that slow motion will be influenced by the rotation. And because of that, the ambient fluid being entrained into the plume is changing its properties over time, and that will see changes the motion of the plume itself. So let me just show you some snapshots from an experiment that was done by Daria Frank of a plume where it's dense fluid coming down from above, relatively fast rotating tank. And after 20 seconds, you see that the plume isn't just going vertically downwards, but it's tilted to one side. 20 seconds later, it's tilted to the other side, and then it's beginning to tilt back. In fact, this plume is precessing. So it ends up going around, basically tilting in a sort of conical motion around the source. So I want to show you that in two movies. Let's see if I can play this first one. I don't know why that one wants to play first, but I'll play them both. The movie on the left-hand side is just a normal plume, no rotation. And it does what you expect, turbulent entrainment going down, spreading linearly as it goes outwards. But you can already see in this movie with the rotating plume, and I know it's not a good image, but you can already see that it's been deflected at this point off to the left, and then it begins to deflect a bit to the right later on. And you can also see that the ambient motion is not this sort of steady, radially inward propagating flow, but you actually have some strong vertical motions in the ambient fluid associated with this plume going downwards. So in some sense, this influence of the plume being deflected due to rotation, I'll say that's now somewhat well established. It's been observed now for the better part of 5 years, both in experiments and simulations. But I want to show you now this sort of serendipitous discovery running a plume experiment. This is sped up 5 times. And you can see this does something different. Instead of tilting off to one side, you begin to see the formation of a somewhat laminar columnar vortex. And after a while, it really settles down, especially when its vortex aligns itself with the source. So this is the phenomena I refer to as a tornado. And the question I want to address here is, why does this form, and under what circumstances allows the formation of a tornado? I'm going to show you that the key parameters here are the source Rossby number and the source buoyancy parameter, both of which I'll define in just a little bit. Let me just show that once again. I want to point out that initially this thing is actually trying to deflect, but still forms that columnar vortex, but then it aligns itself, and that's really when it's quite strong. Okay, so just to define some of these important parameters, this I know is familiar to many of you at Imperial College. First of all, it's the buoyancy parameter. And this is a parameter that basically is a measure of how much the fluid coming out of your source is acting like a pure plume. If you inevitably in an experiment have to drive this plume from a finite size source, and you separately control the buoyancy of the fluid as well as the momentum of the fluid. So some measure of the ratio of the momentum to the buoyancy is given by the source buoyancy parameter. And if this parameter is equal to 1, I should point out here that this alpha is the usual entrainment coefficient. GC is the center line. If you imagine this is a Gaussian distribution, it would be the center line reduced gravity. B naught is, of course, the radius of your source, and W naught is the mean velocity of the fluid coming out of the source. In any case, if this buoyancy parameter is 1, then it acts as a pure plume, and you can track it backwards to a virtual origin that lies below the source. However, if that number is greater than 1, you have what's called a lazy plume, something that was coined by Gary Hunt and Nigel Kay while they were at University College London. Sorry, I keep saying that, Imperial College, my God. See, this is the problem, it's speaking first thing in the morning. All right, anyway, so if you have a lazy plume, what it means is you have a deficit of momentum at the source compared to the buoyancy. So this thing rises, and in fact, if this number is large enough, you actually have a constriction of the sides of the plume as it rises before it begins to spread again. So for a very lazy plume, the virtual origin of the plume far above the source can actually be above where your actual source lies. So that's defining, in essence, the pure plume and the lazy plume. And one thing I'm going to show you is that for a tornado to form, it's more likely if the plume is lazy. Okay, now let's define the source Rossby number. This is defined in the way it's been done for about 30 years now, in terms of the vertical velocity at the source and the radius of the source, and of course the background rotation cast in terms of the Coriolis parameter. And an important quantity here is even if the source Rossby number is large at the source, because the vertical velocity is always decreasing as you go away from the source, the radius of this plume is increasing as you go away from the source, the Rossby number is always getting smaller with distance from the source. So though your source Rossby number might be large, at some distance, the Rossby number locally as a function z of the plume will approach 1. And when it's order 1, you find that's when rotation begins to dominate this motion. It stops spreading outwards in a conical pattern and starts being columnar, sort of dynamics you would expect of rotation influencing motion. And in fact, there were a number of experiments done by Fernando et al. And to be a bit more precise, they worked out this distance from the virtual origin where this plume stops spreading and starts becoming columnar is given by this quantity roughly 5.5 of this, the source buoyancy divided by F cubed to the 1/4 power. Now, this is what happens effectively at short times. If you do a starting plume, it goes down, and then you'll see after it's gone down by this distance, you'll see it becomes calmer. But again, the focus of my talk is not what happens at that early time, but what happens as time evolves and the ambient begins to adjust to the fact that it's rotating. So it's trying to be drawn radially inwards, and hence Coriolis is going to deflect that radial motion. So in that sense, by focusing on the ambient fluid, I'm just going to throw away the nonlinear terms in the momentum equations and just focus on the other forcing terms. So of course, we have the usual Coriolis force that will influence the radial motion. And also importantly here, we'll have the centripetal force, as well, of course, the radial pressure gradient. As for the change in the azimuthal flow, that is dominantly just affected by the Coriolis force. And so if you put in, if you're looking at early times before rotation has had an enormous influence to change things, so you just put in the plume equations and you ask, how is entrainment into the plume affected? Right away, just by putting in the solution of Morton-Taylor-Turner, you can work out that the radial inflow into the plume should go as Z to the 2/3 power over R, where again, this capital Z is the distance from the virtual origin. And this is really one of the keys here. This tells you that the plume is inducing vertical shear in the ambient fluid because the radial inflow is a function of height. So the ambient flow has a vertical shear induced. And yet we know that at least if you're far enough away from the plume, rotation is dominant. The Rossby number of the ambient fluid will be very small, and it's uniform density fluid, so you should have Taylor columns. You should have no vertical structure whatsoever. And hence you have this tension, if you want to call it that, between the vertical shear that's induced close to the plume and columnar motion away from the plume. And that tells you that you're going to get vertical motion induced in the ambient fluid. And I always find this kind of remarkable because if you have no rotation, you just have a plume, then you know that the ambient flow is horizontal into the plume. And if you have a strongly rotating fluid, you know that the motion is purely horizontal. But if you put those two things together, a plume and rotation, you actually then create vertical motion. Okay, so this is one of the important diagnostics that I'm going to show. We've already defined the source Rossby number, but I want to define the plume Rossby number. And this is going to be a function of the height as well as in time. So instead of just characterizing the Rossby number in terms of the vertical velocity divided by F times the width of the plume, and here I'm denoting B theta as the width of the plume, as the radius where we determine the azimuthal velocity of the plume is largest. This actually isn't the dominant thing. What I'm going to show you is in a very short time after the plume develops, that the vertical vorticity within the plume builds up so as to dominate over the Coriolis parameter. And hence really what's going to happen over time is it's the vertical vorticity that's dominantly setting this Rossby number. Okay, so there's a lot of stuff going on in there, but that's the main thing I want to take away from that when I show diagnostics and simulations later. So now let me show you some numerical simulations. This is all done using open source code called OpenFOAM. And I'm not going to go into details about that. People can ask me questions if they like later. All I'll say is that right now I'm showing the full vertical extent of the domain, but I'm not showing the full radial extent. The radial extent actually goes out to 20, whereas here I'm only going from -5 to 5. And also we set it up so that below the bottom of the domain, I actually have a setup kind of like a turbulent plume nozzle with an expansion chamber so as to try to trigger turbulence as soon as this fluid enters the bottom of the domain. And at the top of the domain, I have outflow conditions set to match the inflow conditions. Okay, so with all that as background, let me show this simulation in which there is no rotation. Let me try to show you this simulation in which there's no rotation. Come on. No. It's going to be a pain. Uh-oh, I got the spinning wheel of death here. I'm not sure if you can see that. No one likes the spinning wheel of death. Okay, well, oh my goodness. It's not just me that's fuzzy in the morning. Apparently, it's also my computer. So my apologies for this hopefully brief delay. And that just doesn't want to play. Give me 2 seconds here.
Yeah, no problem.
And just, I had tested this earlier and it played, so let me just go here. I'm just going to try this without presentation mode to see if it plays. And go back to the previous slide. There we go. There we go. Okay, so this is a non-rotating plume. And it does what you expect it to do. It rises, expands more or less linearly with height. The yellow arrows, of course, are showing the motion of the ambient fluid. I stuck a threshold on there so it's not drawing the arrows if they get beyond a certain magnitude, because you'd have monster arrows all over the place. Okay, so that's in some sense a control. Now let me show you a case where it's rotating, but we get that deflection resulting as a result of rotation acting. So again, initially, it looks a lot like our original plume. But I want you to notice what's happening near the source now. The plume is getting much wider above the source, and then bang, you see this deflection. And the ambient motion is quite chaotic. I think it's probably good that I play that again. Whoops. Just go back. So you can see there's sort of a pushing down, that's how I think of it, on the plume fluid near the source that ultimately pushes it off to one side, and then this precession begins. Okay, so now finally I'll show you a simulation where the rotation was such that you get a tornado. Again, it looks like a plume, then you begin to see this squashing down near the source. It even begins to deflect, but then recovers, and bang, you get this columnar vortex developing. I'll play that again, but I just want to point out, you might be worried that these arrows are all going rightward, both to the left and right of the plume, especially around the source. That's because this tornado is actually pushed a bit behind the plane in which I've taken this slice. So really, you're looking a bit at the azimuthal motion going around the plume here. So this isn't going bang into the tornado. It's actually, you're looking at a slice that's a bit in front of the tornado. Anyway, so let me just play that again. Okay. So we are able to simulate getting a tornado, but you can see its formation is not straightforward. It's not just like the plume wraps up and forms a tornado. In fact, what's going on in the source is quite complicated. It's still tilting a bit off axis, just like happened in the precessing case, but then it's able to recover and form a tornado. And that's an important part of this story, because it turns out that even if you run a simulation with identical parameters and you just change the noise conditions at the source, sometimes you will get a tornado and sometimes you will not. The same thing happened in experiments. When we did repeat experiments, we could have all the parameters the same. Sometimes you get it, sometimes you don't. And that all has to do with what's happening as it's tilted. Is it able to recover or not? And in some sense, that's almost a coin toss, although there's a bias to whether or not you're going to get heads, depending on the source buoyancy parameter and the source Rossby number. So that's what I'm going to try and now walk you through some rather dense diagnostics. So first of all, from that movie I just showed you, let me do this time series vertical, not going to the top of the main, but just halfway up to 15 centimeters versus time of this parameter, which I call the Plume Rossby number. So really it's a measure of how important is rotation influencing what's going on inside the plume. So first of all, you see your eye, of course, is drawn to this white patch, which is just the rise of the starting plume. So ignore that. But just below the front of the starting plume, these are dark red colors. So you're dealing with numbers here where this Plume Rossby number is larger than 1. And so initially, there's not much influence. But you can see, especially if you're high up above, it doesn't take much time before this Rossby number has fallen well below 1. And the reason for that is clear, because you have taken ambient fluid at a fairly wide radius surrounding your wide plume and drawn that fluid inwards into the plume, which of course through angular momentum conservation is spinning that plume up. So again, you rapidly reduce the Rossby number with height aloft. But there's another thing that's going on near the source. Of course, near the source that is not so wide, so even if it's entraining fluid, the fluid from the ambient being drawn into the plume across its radius is not going in that far. However, there is a buildup of azimuthal motion around the plume near the source, and that as that builds up, that again is increasing the vertical velocity, vertical vorticity within the plume, reducing the Rossby number. And just for reference, you'll see this later, I've got these two symbols on this time axis. The cross is where we first see the flow be deflected from the vertical, and the circle is we first see the formation of a tornado, which occurs about 3 seconds later in this simulation. So that's sort of the whole ball of wax, and now I want to break it down into its components. Oh, right, I'm still in presentation mode. Let me try and go back into presentation mode here. Okay, so let me try and break this down to components. Here's a time series just looking at the vertical velocity within the plume. Again, you see the starting plume goes up, but what I want to emphasize here is as time goes by, here at this dashed line, I'm drawing a contour where the velocity is half of the maximum. And this is a lazy plume, so the maximum is not occurring at the source, but it occurs about 2 centimeters above the source. In any case, as time goes by, you can see that this contour at half max reduces, it gets closer and closer to the source, which is the idea of the plume effectively being pushed down, if you will, as a consequence of the Rossby number aloft being reduced. When you have a low Rossby number flow, vertical motion is inhibited. And so that low Rossby number aloft is try to keep vertical flow from going upwards. And as time goes by, that encroaches downwards until ultimately the plume deflects, which is the point where the vertical velocity is effectively quenched, try to quench the fluid coming out the source itself. Then we have a pressure diagnostic, and it's the same story here. So normally the pressure, of course, is increasing with height from a low to a high, but that pressure gradient is always getting lower here at sort of the half pressure max until it reaches the source. So again, this is the idea of this rotation is actually introducing an anomalous high pressure that's pushing down towards the source. And finally, the azimuthal flow, where you can see as time goes by, this gradually builds up within the plume. And even after the plume deflects, you can see once this tornado forms a few seconds later, then it really takes off and you get this strong azimuthal flow within the plume, or at this point within the tornado. So those are sort of the diagnostic for what's going on inside the plume. And I want to now begin to look at what's going on in the ambient flow. So here I'm showing you vertical time series, not within the plume, but it's taken at a radius 3 centimeters away from the origin. That 3 centimeters was chosen to be just outside the width of the plume, where it's at z equals 15, at least for the starting plume. So for example, in this flow here of the radial flow, we have ahead of the starting plume, which is more or less this black line, it's first of all pushing fluid radially outwards ahead of the front, and then it's being drawn back inwards behind the front. So that hopefully gets your idea of how to interpret this. The one thing I want to take away from this is that as time goes by, if you just look at the increase in the blue, I'll quantify this more quantitatively later, but the radial inflow velocity is actually increasing linearly with time. And that, of course, is opposite to what happens when you have no rotation, where the radial inflow is just a constant. But when it's rotating, you actually have a buildup of the radial inflow. Also, if you look at the azimuthal flow that's surrounding the plume, you can see these contours of constant u theta are getting closer and closer and closer. And so, in fact, as I'll show you quantitatively later, this is increasing quadratically in time. So this buildup, this swirl surrounding the plume, increases quadratically. I'll also point out this yellow line is trying to plot the ambient Rossby number as a function of height at different times, where this thick yellow line is where the ambient Rossby number is 1. And I guess I'll also point out the interesting feature that initially these things are tilted, but you'll notice these contours become more and more vertical over time. So let me show you from those diagnostics, sorry, not exact from those, but let me show you radial profiles now of the terms that exist in the radial momentum equation. So this is going radially outwards at a fixed height, which I believe was taken 2 centimeters above the source. Showing, first of all, in dark blue, that's the radial gradient of pressure. And in the dashed curve, that is showing the centripetal acceleration. And in the solid black curve, that's showing the Coriolis force. And so the thing that I want you to get from this is that far away from the plume, and by far, it's really not all that far, like maybe 3 centimeters away from the source, which is only 0.2 centimeters radius. That's where Coriolis is dominating the pressure gradient. But within roughly about 1 centimeter of the source, it's really the centripetal acceleration that is setting the radial pressure gradient. Also, as an aside, I'm drawing here as the solid red line, the Coriolis force associated with the radial inflow that, of course, is going to be driving an azimuthal acceleration. And I just want to point out that these things should be, this is a log-log scale. And so really you are, if it was not rotating, should have a -1 exponent. But in this rotating flow, in fact, it's not -1, it's -0.5. And that is another indirect indication that there must be vertical motion within the fluid. Because if there was no vertical motion, mass conservation on its own would require UR to have a -1 slope. Okay. I don't know about you, but this is a lot even for me to absorb at 8:30 in the morning, but hopefully you've had your tea already and you can absorb all this. It's the frustrating thing about Zoom. I can't see people's faces to know I've lost you, you're falling asleep. Hopefully you're hanging in there with me. I just gotta, all right, thanks, Jonathan. I appreciate the heads up. Okay, so I just have a few more diagnostics to show you here. And this is really quantitatively showing the temporal evolution. So here I'm showing in time, again, outside the plume at a radius of 3 centimeters away and 2 centimeters above the height of the source, I'm showing how the azimuthal velocity evolves in time. And here you can clearly see, yes, indeed, it is increasing quadratically in time, while the radial inflow velocity is always increasing linearly in time. And of course, I say increasing, but it's increasing negatively, going inwards into the plume. This is maybe the more relevant diagnostic, looking at the time evolution of quantities within the plume at this height of 2 centimeters, which I don't think I mentioned is more or less the location of the virtual origin of this lazy plume. So as time goes by, you have within the plume more or less a linear increase in the vertical vorticity as well as the maximum azimuthal velocity. The vertical velocity within the plume really does not change much until shortly before this time where the thing is deflecting. These two quantities are building up, and all the time the adverse pressure gradient is encroaching down upon the source until very rapidly the vertical velocity at this height of 2 centimeters decreases and becomes incomparable to the azimuthal flow. This is that point. That cross here is indicating where this thing deflects. Here I'm actually representing everything in non-dimensional time units. So this is roughly at a time of ft8. And the tornado then forms at this later time. And when that happens, that's where, again, you see this azimuthal velocity begin to take off, as well as, of course, the vertical vorticity. Okay, so now is another diagnostic, and this is me really trying to get to what's going on. What is it that allows a tornado to even form? I want to begin to look at, if a tornado forms, is it stable? So maybe the conditions are right, you can form a tornado, but it might not be stable. And so one way to get us towards that is, first of all, to look at the results of 4 different simulations in which a tornado formed. So here I'm showing these different parameters, changing the source volume flux and changing the background rotation rate. And what I'm plotting here is the maximum azimuthal velocity within the tornado as a function of height. And the key thing I want you to notice here is going upwards. This thing is in all cases getting moderately smaller with height. But the most important diagnostic is to compare that quantity, the azimuthal velocity, to the vertical velocity within the plume. This is a quantity known as the swirl. It's also a quantity that appears in studies originating from bachelor's study of wingtip vortices, and then people more ideally looking at the stretching of vortices as, if you want, as an atom of turbulence. So the key here is we have vortices that are not just passively sitting there, but they're being stretched in the axial direction. The stretching, of course, is going to want to bring this, make this vortex tighter. But on the other hand, if it's not stretched enough, the azimuthal flow is going to want to spread outwards through an instability. The parameter that's used to characterize whether or not a stretched vortex is stable is given in terms of this swirl. I'm using the swirl parameter in a slightly different definition than it's been done in the literature, for example, by de Rembla and others. I've defined it in a way based in terms of the maximum azimuthal velocity. And it defined that way, if this quantity is larger than 1, then the tornado is stable. And so you see in all of these simulations, the swirl parameter within the tornado is just above 1, at least up to some heights of 5, and most of them above 1 up to 10, except for this blue simulation with relatively slow rotation. So you need to have conditions correct in order to form the tornado, and the tornado itself has to have properties such that its swirl is large enough, that you've built up enough azimuthal flow within the tornado near the source compared to the vertical velocity that it can actually maintain its tightness. Okay, so again, that was a heck of a lot of analysis to absorb, and I'm going to try to summarize it through a sequence of schematics to hopefully put a picture in your head. So this is what we're imagining happens at an early time. We've started the plume, the front is way up here. It doesn't affect the dynamics of what happens at later times. at some height above the plume, which is where the Rossby number associated with the plume would be order 1. That's where we begin to see rotation influencing the plume. And associated with this strong rotation is an inhibition of vertical motion. So in some sense, you can think of that as providing a force that's preventing fluid from below from continuing to rise. Consequently, the plume widens with height. All the time, it's still entraining fluid, but as it entrains fluid from this wide radius, rapidly carrying it into the middle, that's a very big change of rotating ambient fluid that's been carried a large radial distance inwards, which again acts to spin this up efficiently. So that provides an even stronger retarding force that is encroaching downwards on the ever widening plume. I'm also sketching here all the while in a more subtle way, we have a buildup of azimuthal velocity around the source. And then finally, this adverse pressure gradient has built up enough that it's pushing on the fluid emanating from the source itself that begins to push it off axis. But as soon as you push it off axis, you're providing a stretch because this is not going vertically upwards, now it's going out at an angle, and so this fluid can shoot out at say a faster rate, which can impulsively create an even faster spin up of the fluid. And this is where the coin toss comes in. It is possible at this point that the ambient motion that's pushing off axis, as well as this downward force pushing off axis, just keeps it off axis. And then it starts to precess. When that happens, you're done. You'll never see a tornado. However, if that impulsive bit is enough to spin it up and create a stable tornado, then it can reinforce itself. And now you have this circumstance where you have a more or less quasi-stable azimuthal flow surrounding this tornado with rising motion that's causing the stretching within the tornado. So that is the summary picture of what's going on. I have to say it's been a battle with this problem because it was such a chicken egg problem. The plume affects the ambient affects the plume. Which one is dominant? And really all these things are happening together. And it doesn't help with the added frustration that you have multiple equilibria, one where a tornado can form and one where it can't. And it's almost purely random. But it's not purely random. I qualified it by saying almost, because if you do a number of experiments where you vary in different experiments the source buoyancy parameter and you vary the source Rossby number, one thing you see is this. Remember that it's a pure plume at the source if the source buoyancy parameter is 1. It's a lazy plume if this is larger than 1. And we more often find tornadoes that form if this source buoyancy parameter is larger than 1, if it is a lazy plume. As for the source Rossby number, there doesn't seem to be a clear cutoff one way or the other, but it seems pretty clear that you'd want to have your source Rossby number much larger than 1 so that rotation's not influencing it as it comes out the source. It still has that sense of entrainment and turbulence, and only does rotation affect it high up enough above the source. So you want the source Rossby number to be larger than 1 or 1 over that value to say being on order 0.1 or below. The other thing is, of course, you could go to having your Rossby number being infinitely large, effectively no rotation, and then you know that you're not going to get tornado formation. So there's a range here somewhere between your Rossby number being greater than 10, 1 over that being smaller than 0.1, and it being not too small, that ambient motion, and here I'm going back to the real problem of ocean currents influencing, say, the deep water rise in oil plume, ambient motion trying to tilt the thing off axis anyways. Okay, so in short, we're proposing here, based on the simulation results as well as what we saw in a number of experiments, that you need to have a lazy plume with sufficiently large source Rossby number, because when that's the case, If it's a lazy plume, you already have a bit of a vertical stretch of the fluid in the plume near the source because it's constricting before it widens again. That's already going to give you a sort of spin up happening within the plume. Also, for a lazy plume, turbulent entrainment is reduced. It's not shut off unless it's a super high source buoyancy parameter, but it is reduced. So you already, in a lazy plume, it's not quite as turbulent, let's say, as you have with a pure plume. So you have a slightly more laminar, if I can use such phrase, slightly more laminar source fluid that's also being stretched. So there is a sense of preconditioning it to enable a tornado to happen more frequently. Okay. So I hope you're able to hang on to most of that. I'm just going to end off with these pictures. And to be honest, I've been looking at names and pictures and not faces for a while. So I think I'm just going to end on those conclusions and take any questions at this point. Thank you very much for your time.
Great. Thanks, Bruce, for that interesting talk. So we're going to open the floor for questions and discussion. Just raise your hand or unmute yourself and ask a question. So while people think about it, let me ask one. So the movie that you showed that didn't want to start, it somehow seemed to me that it starts out quite convectively unstable, and then it sort of drifts back to more like the exit of the jet, and then violently actually changes. Is there any possibility that there is a hidden absolute instability somewhere close to the nozzle?
I've not thought of it in those terms, Peter.
Yeah. Okay. So you showed the onset. That's the movie that didn't want to start. Yeah, exactly, that one. Yeah.
The one that forms a tornado eventually, or the one that just persists?
Exactly. That forms the tornado eventually.
Okay. Again, I'll just.
The one with rotation, with background rotation. Yeah. Exactly.
Yeah. Okay. So maybe you can just tell me to pause.
Yeah. So this one first develops very convectively. It's very straight. You know, it breaks up quite high up, and now it's gonna eat its way back towards the entry, and then now it actually goes quite differently afterwards. So is there a possibility that there is actually a hidden absolute instability close to the nozzle, and it just needs to reach it with some kind of a perturbation before the feedback loop kicks in and actually contaminates the entire jet?
Well, so I'm not going to say no to that, but I'm not sure that even thinking in those terms would help, in the sense that even if there is an absolute instability, then it presumably would have a very short time scale for growth. And so you're looking at a time evolving flow that's already, you can already see that it's you know, shortly before this time, it's doing things to try to affect the source. And then maybe like in a half second, if it is some kind of absolute instability that's kicking in, kicks it off. In my mind, well, it was something was going to happen anyways, because you had this. I describe it as an adverse pressure gradient pushing down on the source.
Yes.
So, yeah. See, this is why I would wish I was at Imperial right now, right? Because then we'd have a cup of coffee and we could really hash this out.
Exactly. Yeah.
Yeah, I can't quite get my head around the question. Like I know words that you're saying, but how you'd actually model this to come up with that. But
it's a highly unsteady flow. So you know, anything that you do with some type of instability analysis would have to rely on some scale separation, and in that case you would actually look for fairly high growth rates that justify, you know, considering what you linearize around as frozen. So I think that's the challenge. But it just watching that behavior, it somehow reminded me of some kind of a bifurcation switch between something convective to something absolute. That's what I'm asking. Yeah.
And that's where I follow what you're saying. Instead of, you have all these turbulent eddies that are just being vectored away when it's a normal plume. Suddenly they're kind of staying in place and they're allowed to grow in place.
Exactly.
So that's why I understand the terminology of what you're saying.
Yes.
But in terms of how to model that, and if that would actually give you insight into, why it, say, breaks symmetry and goes off axis.
Yeah.
Especially again because of that separation of time scales, as you mentioned. Everything happens so fast in terms of the evolution of the fluid near the source, as well as it's suddenly being kicked off axis.
I mean, the precessing motion would probably come in as an n is equal to 1 instability, right? As a helical mode.
Yeah, and it's funny, like a lot of people have noticed the precession, but I don't think there's a fundamental theory to predict the precession. People do, from measurements, they know that the precession, I think it's about, the period of the precession is about twice a rotation period.
Oh, okay.
So there's something predictable about that, but now it's only empirical. I don't think it's theoretical just yet.
Yeah. Okay. All right. Are there any other questions from the audience?
Bruce, I was wondering if you could say something about what happens in longer times with your once your tornado is formed, because everything, as you said, is increasing linearly or quadratically. What happens if you wait a bit longer? I guess it's bounded by the tank, is it?
Yeah, I'm glad you asked that. So in the simulations, when the tornado formed, they would remain stable for about, I'll say on the order of 10, 20 seconds. In the lab experiments, which did have a larger radius domain, so in the simulations, my domain goes out to a radius of 20 centimeters. In Lyon, our experiments went out to 45 centimeters. In those cases, when a tornado formed, it would remain stable for up to 3 or 4 minutes. But eventually, inevitably, it would always break down, go off axis, and start to precess. And once it started to precess, that was it. You would never see it reform. So the stability of the tornado, it's hard for me to judge, but based on comparing simulations to experiments, the stability of the tornado does seem to depend a bit on the domain size. This is, when you think of all these turbulent motions, if I just sort of get this playing again, and you look at all these turbulent motions aloft, and it's in a confined domain, so you're going to have now some vertical motion going up the sides of the domain. That's going to influence the circulation taking place near the source. And that's why this, I think, eventually gets kicked off axis. In a wider domain, that influence of the side boundaries would be smaller. And so the tornado, I think that's the reason why the tornado lasts longer.
So in a theoretically infinite domain, it could be permanent then, or except
yeah. So in a theoretical infinite domain, so let's say the Gulf of Mexico, it could be permanent. But the problem is, in a realistic infinite domain, there's always background currents, eddies, tides, and any of those background ambient motions can overwhelm what's happening near the source, kick it off axis. And again, as soon as it goes off axis, you're done. It will never reform into a tornado. At least in no experiments that we saw did that happen.
Fascinating. Yeah, thanks, Bruce.
At some point, I should have taken selfies of us doing these experiments, because every time we did one, we'd all be walking around the table, watching it, being turbulent plume. Okay, it's getting close to the source now. And then if a tornado formed, I mean, it was like we were at a football match. There would be like all of us, yay, tornado! It was very, very exciting experiment.
In practice, you often see these things drifting, translating sideways. I mean, I'm not sure how that fits with your idea of your source at the bottom. I mean, is it just once they form, they do something else? Or
you're thinking more of a sort of classic tornado from an atmospheric storm. I think one of the main differences between the tornado and these experiments and simulations is that there's a buoyant source.
Yeah.
So you have buoyant fluid rising, which is providing that vertical stretch. And that's different, of course, from what you would have in an atmospheric tornado, where you don't have, say, warm air rising upwards through the tornado. It's more something that originates from the cloud top, where you already have something like a cyclonic mesoscale storm that concentrates and then descends, but that's all pressure driven and there's no buoyancy involved in that. So I think a big chunk of this, it has to do with the vertical stretching that's keeping the tornado stable. And that vertical stretching is largely due to the fact that the core is buoyant. Yeah.
Yep.
Good. Any other questions?
Yeah, I have one. In the simulations, do you ever see any kind of high velocities, high speeds? Because you mentioned the swirl, and I'm kind of thinking if this is a good setup to almost generate singularities of the Euler equations, because you usually need. I mean, it's a necessary condition to have the swirl.
Yeah. I guess in some sense, in terms of the azimuthal velocity, or if you want thinking of it as a proxy for the vertical vorticity inside the plume, typically we find that is moderately larger than the vertical vorticity, but it's not massively larger.
Mm-hmm.
So in that sense, it's not like you're creating something like a singular vortex, if I'm trying to get my mind into the way you're thinking. So I think there is a limit to how fast these flows can get. When I'm saying that, I'm thinking of that swirl parameter that I introduced, which is the ratio of the azimuthal velocity to vertical velocity.
Yeah, because
that number is
had a
typically
little
bigger
spike.
than 1, but we only see it's
Yeah.
between like 1 and 2. We never saw it being a value like 10, implying massive swirling with relatively little vertical flow.
Okay. Oh, I thought it went to about 5 or something. There was a black curve.
maybe it did. Maybe it did. And I'm just.
That's what.
Yeah. Okay. So
Oh,
yeah,
yeah,
near
4.
the base, I guess it
Yeah.
got up to about 3.5 or 4.
Yeah. Yeah.
Mm-hmm.
But yeah. But yeah, I don't think you'd see such a massive swirling compared to the vertical flow up the center,
Yeah.
that you could, in some sense, ignore the vertical velocity and just treat it like a singularity.
Yeah, and I guess the simulations are Navier-Stokes anyway, right? So there's probably viscosity somewhere.
Yeah, though of course in simulations you can always reduce the viscosity. In fact, I didn't mention this, but the simulations are actually performed with a kinematic viscosity that is 1/10 of realistic viscosity, which we only did because we used realistic viscosity. The plume was too laminar rising from the source. It only broke to become turbulent about 5 centimeters above the source. So we artificially reduced the viscosity to have it turbulent leaving the source. And there's nothing to say we couldn't reduce it further, but of course, yeah, well, it's just more computation intensiveness, but.
Right, thank you.
Mm-hmm. Any other questions? Oh, Graham, please.
Oh, now I'm in trouble. Now I'm in trouble. I was dreading this.
Not at all. Thanks, Bruce. I think my question perhaps stems a little from Jonathan's, and I was wondering to what extent do you think the instability might be affected by perhaps the ability of the source to move around in some sense? I mean, suppose it was a really lazy plume from a large aerial source, and you're able to change the point at which the buoyant fluid feeds it.
Oh, it feeds a tornado.
Yeah.
Yeah. I'm going to give a cop-out answer and just say I'm not sure. One thing that I've talked about is that when it's a lazy plume, very lazy plume, you have virtually no entrainment near the source. And I was hypothesizing, so it's already kind of laminar near the source. But on the other hand, if you shut off entrainment, you've also removed that buildup of vorticity within the plume near the source, because you're not entraining this linearly growing radial inward velocity. Or for that matter, you have the azimuthal velocity growing outside, but only because it's in training. If you shut that off, none of that occurs. And so I don't know what the limit is if your source buoyancy parameter gets so large because you've shut off entrainment, maybe you'll never see a tornado then. But because it's laminar, maybe it's easier. And so really that's set up for new experiments or simulations to explore, I think.
All right, thanks.
Since I remember Gary actually did some lazy plume experiments back 15 years ago there. Hopefully you still have that set up. Who knows? You just have to get your whole lab rotating quickly.
Good. We have a question from John.
Hi, Bruce.
Hi, John.
Thanks for the talk. It was very nice. You've successfully distracted us all from marking, so that's very good.
My job is done.
So I have a question actually. So it relates to what I think you were just talking about with Graham. So would it be worth considering what happens to a rotating fountain, so that you can, because I think the difficulty with lazy plumes is that it's always impossible to separate the laziness as quantified by your buoyancy parameter and the necessarily laminar-like effects that occur close to a source. But if you had something like a fountain, you may well see buoyancy parameters that are very large, but not associated with the laminar like behavior that you would get above a source. So it's just with plume theory, it's always very difficult, I think, to understand lazy plumes, because plume theory doesn't really account for the laminar effects near the source.
I guess I mean, no one's done those experiments as far as I know. My feeling is if you have a fountain, then of course at the source it's momentum driven, which then kind of already goes against what we were seeing with plumes, where you really want it to be buoyancy driven. And the other problem you would have with fountains is, of course, that it then falls down and rains around itself, which changes in a different way what the ambient flow is doing. And it would be interesting because, of course, if it's rotating, it wouldn't just rain down to the bottom. You might end up having this sort of columnar motion that, if I think about it, would be somewhat anticyclonic. So that would certainly introduce a number of extra things that are not in this study. And so my gut feeling is you would be unlikely to see a tornado, but with so many different things going on, is not to rule out the possibility. Maybe it could.
Yeah, I guess I was ignoring the core and thinking of an upside down fountain, so still positively buoyant fluid, and just looking at the shell that then rises, so treating what would normally be the rise height as the kind of source, and then seeing whether I don't know whether you'd see a tornado, probably not, but it's just might be a way of understanding buoyancy parameters in a different setting.
Okay, and I think that way I would be very doubtful that you would see a tornado from, say, this umbrella that's trying to go back downwards. And the reason I say that is I'm thinking back to Fernando's experiments with plumes again, where it rose, and after it reached a height where the Rossby number was order 1, the fluid became columnar. That would be the equivalent of what's happening. Once this forms this umbrella and starts to come down, that fluid up there has a Rossby number of 1. And in Joe Fernando's experiments, then you would see that this would be a rotation-dominated flow. You might see the thing rotating and breaking up into baroclinic eddies. I shouldn't say baroclinic, but at least columnar vortices. But you wouldn't see that retightening that you need to get to have this swirl build up and form a stable tornado. I think you just have sort of a large scale things on the order of some deformation radius, just evolving passively. Yep.
Right. Any more questions from the audience? No, doesn't seem to be the case. So thanks everybody for coming, and especially thanks for Bruce. Very nice talk, and thanks for
Good talk.
getting up early and accommodating our time slot.
It was a great pleasure to see you all again, especially to see many of the faces of old friends of mine.
Yes,
Hopefully I'll see you again soon.
hopefully we can see each other soon in person.
Indeed. Wow.
Thanks a lot.